So lecture number 3, problem solving and search strategies. Last time we talked about rational agents and said that rational agents maximize performance. In the simplest case, a problem solving agent is just going to satisfy a goal condition. So in one type of problem, we may just want to say something like, is it possible to do this? Can we satisfy some condition? So for example, can we solve a Sudoku puzzle? Can we solve a crossword puzzle? Or can we reach the end of a maze? A problem-solving agent is a type of goal-based agent, and the output of this agent is going to be to find a sequence of actions that satisfies the goal. So the simplest type of problem is a simple, can we satisfy this goal? And the next type of problem, which is a little bit more difficult, is can we optimize some sort of cost of that goal? Like we talked about last time, can we optimize the performance measure, not just say whether or not something is possible? So here we go. Here's an example scenario. I know that the text here in class is a little bit small, but this is a map of Newfoundland. I realize not everyone in class is super familiar with the geography of Newfoundland yet, but we're about to get a little bit of a lesson. So here is an example. So a tourist comes to Newfoundland and they land in St. John's. So St. John's, of course, is this big dot over here. It's the capital of Newfoundland. We're the easternmost city in North America. So you should know where St. John's is because you're physically here, right? And you want to go to one of either Port aux Basques, which is down here in the very, very bottom left, so the southwest of the province, and that's where you would get the ferry to the mainland of Canada, or you want to go to St. Anthony, and St. Anthony is very, very far in the north. So in this problem, we want to go from St. John's to one of either Port aux Basques or St. Anthony. That's the goal that we've given. We may have extra constraints on that problem. So for example, maybe we only have 10 hours to make that trip. And if we do, maybe one of them is possible and one of them is not possible in that amount of time. Or we only have a certain amount of money for gas. So within a problem solving, even if it's just a goal satisfying problem, there may be other constraints that we have to talk about, right? And the way you can incorporate that into your search algorithm is just, hey, if this does not satisfy our constraints, then it's no longer a viable solution to the problem. It's pretty easy to implement constraints. So now we have the goal formulation. So in this case, the goal is a set of states in the environment. So we have a state representing St. Anthony, we have a state representing Port aux Basques, and the goal is going to be satisfied if one of them is reached. And what that means is, if a sequence of actions leads us from the starting state of St. John's to the goal state of either St. Anthony or Port aux Basques, then the goal has been satisfied and we say that the problem is solved. Because in this case, the problem being solved means just, okay, give me a path to either one of them. But in this case, the goal is one of a state that may be many states in a set of goal states, but in general, the goal can also be a function evaluation, right? This is the easiest possible case where it's just pick one of these possible states, and if we're there, then it's satisfied. But it could be, for example, in a video game, if the enemy health is less than or equal to 0, meaning you've killed the final boss or something. For something like chess, it would be if the enemy player or the other player is in checkmate. That's something that you would have to test for. Or if the player has all the pieces of the Triforce and Ganon is dead, these arbitrarily complex functions for solving problems in general. So the goal in this case is just a state, but in general, the goal could be a more complex function evaluation. But now what we have to do, in order to solve this problem with a computer, we have to well define the problem, right? So the first thing we may wonder is, what states do we consider in this problem? Do we consider, for example, only the towns in Newfoundland as states? Or do we consider like every square meter in Newfoundland as a state? So for example, let's just say you're walking this, right? Just to make it simple. So if I walk from here to here in this problem, is that considered a new state or not, right? If I was pathfinding from here to the outside of this room, I would probably choose a state representation that was something along the lines of maybe every square foot of every square meter or something like that, so I could navigate to that door, which is locally close. But if I was talking about going from St. John's to Port aux Basques, it may be overkill to describe that path in every square meter that you have to travel from here to Port aux Basques, right? So you have to decide, first, you take your environment and you decide on what the state representation will be. If you take a game like crossword puzzle or something like that, it might be very obvious what a state is, right? So you have a state of the crossword puzzle, and if you've changed any letter in the crossword puzzle, then it's a new state. But sometimes you may want to be more fine-grained or coarse-grained with your state depending on the problem. So with that, the states that you consider are also going to influence the actions that you can take in this problem, right? So if you've chosen every square meter in Newfoundland to be a different state that you're in, then maybe your actions are now move left by 1 meter, or move north by 1 meter, or move south by 1 meter, right? But if you've chosen the towns in Newfoundland, then moving left by a meter no longer really makes sense as an action, because an action takes you from one state to another state. So maybe you say, okay, I'm going to take the towns in Newfoundland as my states, and let's just assume that the person is capable of navigating from one town to another town via the roads, right? So maybe we'd formulate this as like a graph, and if there are no towns in between two towns, then you just go on the road between those two towns, and that's how you would define your action. So for example, you might say, well, in order to get from St. John's to Port aux Basques, you would go from St. John's to Clarenville, Clarenville to Gander, Gander to Grand Falls, Grand Falls to Stephenville, and Stephenville to Port aux Basques. Maybe that's your sequence of actions. And then you can maybe assume that the agent carrying out those actions is capable of doing those actions, right? Similarly, if you had chosen move left by a meter, then your agent has to be capable of measuring its distance of going by 1 meter. So the choice of states and the choice of actions is, in this case, it might be obvious, but in other cases it may not be so obvious. And also, what sort of information is stored in a node? And we'll talk about what nodes are later, but essentially you're going to formulate this as a graph problem. And then each node in the graph is going to maybe store some information, like where am I currently? Am I at this town? Am I at this particular XY location? How long have I driven so far? How much money have I used so far? So all of these things are considerations in the problem. So a well-defined problem is going to consist of a few different things. First, it's going to be the initial state that the agent starts in. You've got to tell the problem, okay, here's where you're starting. The actions that are possible from each state. So in this problem, like I said, you're either going up, down, left, or right by a meter, or you could go between towns, whatever. The set of goal states also has to be well defined, or the goal testing function, whichever you're using, and also the action cost function. So if you are minimizing a cost on a path, then that may be, so each action is going to have a particular cost, and then the path, which is going to be a sequence of ordered actions, you're going to sum up the cost of all of those actions to get the cost of the path. And then, for example, if you're trying to minimize distance, then you might try and find the path which has the minimal distance or something like that. So here's an example problem definition given this environment that we're in. The initial state is going to be St. John's. Maybe we have chosen that the actions are towns that are directly connected by roads. The goal is going to either be St. Anthony or Port aux Basques, written there in short form. And the action cost function is going to be maybe travel distance, maybe time, something like that. So this would be a well-defined problem that we could then put into an algorithm to try and solve somehow. So that's the problem. What is the solution to that problem? Well, that is going to be a path. So whatever algorithm you write is going to output a path from the initial state to the starting state. Now, to the goal state. In some environments, a path is a pretty intuitive way of describing this. When you're talking about directions, for example, directions are often described as a path. But other things like solving a crossword puzzle or solving a Rubik's Cube, an ordered sequence of actions that you take is still called a path, even in those domains, even if it doesn't represent a physical path through the environment in like distance. So a path is going to be from the start state to the goal state, and it is an ordered sequence of actions. And the order of the actions really does matter. So for example, if I was here, if you told me to go forward and then left, I would end up in a different place than if you told me to go left and then forward, right? Because there's a desk in the way. So the ordering of the actions does matter. The solution cost, and cost is typically a word we associate with bigger meaning worse, right? Cost is something we have to pay, therefore we try and typically minimize cost. And so that is the sum of the cost of the actions, typically, in this course it will be. And most problems are going to assume that the costs are all greater than 0. Why? Well, mostly for our sanity. Because if the costs could be 0 or less than 0, well, if they're equal to 0, then we could keep taking those actions and the cost of the path wouldn't go up. And then our algorithm could basically loop infinitely and it would be terrible. And if the action costs were less than 0, then we could take more actions to get a better path. And that wouldn't be, we're not going to deal with those theoretical things. So for the whole course, when we're doing search, we're going to assume that all of our action costs are greater than 0. Okay, just for simplicity's sake. And therefore, the optimal solution is going to be the path with the lowest path cost among all possible solutions. So if you could find all possible solutions and then look over all of them, you would take the one with the lowest cost, and that would be the optimal solution. Now, as you may have guessed, especially if we're dealing with paths in real life, there are oftentimes many, many optimal solutions. Right? If I go right, right, up, up, maybe that's the same solution as up, up, right, right, and they'd have the exact same path cost. It doesn't always work out like that, but there can be many optimal solutions, and an optimal solution is just one of the optimal solutions. Okay? And with assignment 1, you will find that there are going to be many, many, many optimal solutions for any given path that we find. And so what I'm really interested in that assignment is the optimal cost. Because even though there are many optimal solutions, or maybe many optimal solutions, there will only be one optimal cost, right? And all the optimal solutions will have the same optimal cost. Okay. So let's look at an example graph problem that's a bit more abstract, and I'm sure you've all seen problems like this before, and I'm sure you've all seen things like breadth first search and depth first search, but what I'm doing here is setting up a framework for the more complicated searches that we'll do in the future, and I hope that eventually what you will notice by the end of maybe the A-star search algorithm lecture is that, oh wow, even though we've seen that stuff before, I've never seen it phrased in that way, and you can really get a feel for how all these algorithms are actually related to each other, and how really simple they are, and how you need minimal changes to change one of these algorithms you may never have thought was related to this other algorithm. It's one line of code difference. So that's why I'm going through all of this background information. It's to set it up in this way. So in this problem, we have states over here. So these squares are states. I made them squares because I'm going to use circles for nodes, and I just wanted to differentiate them. So this is a finite graph, meaning there are a finite number of states and a finite number of edges between those states. So this problem, these are states, not nodes. Okay, so typically we would say there are nodes in a graph, but we'll show nodes in a second. So I have state A. This would be like being in St. John's if you were in state A. And then there are actions between these states. So for example, if an edge between A and B exists, then it is legal action to go from state A to state B. That's what this graph is representing. So for example, we can travel from A to B, we can travel from A to D, but we cannot travel directly from A to E because there's no edge between them. The goal state here is goal state C. I've got the starting state red and the ending state green, so apologies to colorblind people. Maybe I should have reversed those colors, but that's just how I've done it here. And the action cost function, we have an edge label. So here, for example, going from A to B is going to cost us 6. And now the abstract algorithm doesn't care whether 6 means distance or time or money or a number of friends you meet along the way. It's just the cost that we have decided. And the tangible meaning of that cost in real life obviously doesn't mean anything to the algorithm. So if I gave you this on an exam and asked you to analyze this in terms of this environment's properties, you would say, that it is fully observable. There's no hidden information. It is static. It is discrete, deterministic, single agent, and sequential, right? So those are the properties we talked about last time, and that's a perfectly fine exam question, this sort of thing, to be able to ask you. So let's talk about the objective here. Maybe our problem asks, is a path to the goal possible, right? So it just asks, satisfying, can I get to the goal from this location? Or maybe it would ask something a little bit more complicated, what is the shortest path to the goal? And the shortest path may be in terms of the cost of the actions, it may be in terms of the number of actions. You've got to be very specific when you ask that. But typically, when we say shortest path to goal, it's the shortest sum of action costs that are denoted by the edge weights here. So, which algorithm are we going to use for that? Well, hopefully, midway through this course, you'll have been shown a number of algorithms, and you will be able to choose which algorithm you want to apply. But the family of algorithms that we're going to apply is called search. Okay, so that's what we're going to talk about, is what is search, why is it important, why is it really cool to do. So what is search? Well, at any given state in any environment, an agent may have several available actions, right? There are some states that are terminal that have no actions, but let's just pretend it's a normal state where I can choose to move up, down, left, right, I can choose to jump, I can choose to shoot, whatever. I have some number of actions that are available to me. The agent can explore various sequences of those actions. So I'm going to try maybe going up, then left, then right, for example. And the agent, after it has explored various sequences of actions, is going to choose the best sequence that it found. And this process, in general, is called search. Try a bunch of things, choose the best thing that you try. That's it. Now, when I say try a bunch of things, the algorithm may not actually need to move a robot in the real world, right? You may have taken the problem, translated it into here, and it just finds a path for the robot, and then the robot is going to follow it. It doesn't need to actually physically try those things. But you have expressed your problem in terms of this environment, and then the agent within that environment is going to see what it can do in that simulated environment. So search is going to explore the problem state space. We talked about state space last time. That's the number of possible different states that there are. So an agent is going to take an action in a current state. That's going to transition us to another state. So it is going to explore some subset of the state space of that environment. The process of doing search is going to generate a search tree. And we'll talk about that in a bit. I have an example. And this tree is going to have nodes and edges. Okay? So what we showed before, up until this point, is this is the environment. It has states, and it has actions between those states. So I can travel between state A and state B via this action, and the action has this cost, right? I have just chosen this representation for expressing that environment. Depending on the environment, you may have a map of Newfoundland to express your environment. It may look different than this expression of this environment. However, over here, we are going to show the nodes in a search tree. And so that's what I'll show now. So search has a couple of processes in it. I'm going to show it visually, and then I'm going to show the pseudocode of the algorithm so you can really get a feel for it. So we're going to start out in state A. That is the initial state of the problem. And so the initial node that we create to search from is a node that is representing state A. And I'll show in a bit that these nodes are going to have other data associated with them. For example, you may have the distance that I've traveled so far. That may be something you want to keep track of. You may have the parent node of this so that you can backtrack and get the path. But these circular nodes over here are different than these square states over here. That's the important part to notice. If you wouldn't mind silencing your phone, that would be great. So the first thing we do is a process called expansion. So we're going to take a node and we're going to expand it. And what expanding means is if I look at the state of the environment that corresponds to that node, so this node over here is representing state A, then the process of expansion says, what are my legal actions at that state? and generate a new node for each neighboring state and put those nodes into the tree search. So over here, for example, it's legal for me to go from state A to state B and from state A to state D. So after I've expanded A, then I have this graph right here. Okay? Now, which order we expand them in, that is a topic for another time, but we have chosen some arbitrary ordering for the expansion of those legal actions. So here's the tree that we have now. We have AD and we have AB. It's very easy to look at this graph and, for example, call this node D. But it is not node D. It is a node in a search tree, and the state of that node happens to be state D. Okay, so let me go through another little bit, and then I'll explain this a bit further. So now what we're going to do is we've expanded all of A. So now we are going to, or we've expanded the root node. Now we're going to choose another node, maybe at random, whatever, to expand next. So we're going to expand this one on the left because it's a little more convenient for me to write on the slide. So we take this node AD, and then we expand that one. And D can go to A, to B, or to E. So we create nodes representing those actions between those states, and we create new ones. Then we expand this one, we go to this one, etc., etc. So this is the process of searching. You are creating this ever-expanding search tree, which has nodes representing actions that you've taken through states of the environment. And then you continue until the goal is found. So once you have, and depending on the algorithm, this is a little different, but essentially, once you have a node that represents the goal state, then you have somehow found that state. Okay. And just realize that this is very important, and sometimes some people miss this. These are states of the environment, and these are nodes in the search tree. The state space here is finite, right? There are 5 states. There are 1, 2, 3, 4, 5, 6, 7 edges representing legal actions at those states. So that is a very finite search space, or state space. But the search tree is infinite, right? We can think here, I could go, like if I keep doing this, AD, 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 it's infinite. So this search tree right now is of infinite size. So they are very, very different things. They just happen to look the same in this example. So let's look at an example that isn't so similar. This is called the sliding tile puzzle. Up here I called it the 15 puzzle, but this isn't actually the 15 puzzle. This is the 8 puzzle. So what happens here is you've got this jumbled up puzzle. Has anyone ever played this puzzle before, physically, or in a game? Yeah. So what you do is your legal actions here at any given, this is a state of the problem. And here I can slide the 8 over, I can slide the 4 up, or I can slide the 6 over. And then the game is going to give you in its instructions some configuration of a goal state that you're trying to reach. So here it's trying to put the, different versions of this might have the blank in the top left, the bottom right, or in the middle, or whatever. But there's some goal state that we're trying to reach through a sequence of actions. And so here is a visualization of a search tree through the state space of the sliding tile puzzle, right? So we started up here at some state, some random jumbled up starting state. And so our legal actions here are to move the 6 down, the 7 over, or the 5 over. So this is moving the 7 over, this is moving the 6 down, this is moving the 5 over, right? Then from each of those, we have a certain number of legal actions. In this particular example of the search tree, they've eliminated the duplicated actions, right? So here, for example, it says there's only one legal action, but in reality, we could move the 5 back to where it came from. That's also a legal action. It's probably just not a great action. And then we see, at some point, we have reached the goal node. And so, or a node representing the goal state. And here, this goal happens to have, instead of like 1, 2, 3, 4, 5, 6, 7, 8, 9, it has 1, 2, 3, 4, 5, 6, 7, 8 around in a circle, right? So whatever the goal state happens to be, this is just a nice visualization of the process of searching, the looking at the legal actions, generating the next state, creating a node based on that state, and building up this search tree. So the remaining question is, when we have nodes in the search tree, which node do we expand next? And it turns out that choosing which node to expand next makes up the difference between the vast majority of search algorithms. Just this one part. The rest of the search algorithm is almost identical. But it's how do we choose which node to expand that makes up the majority of the difference. So let's have a look. Oh, but first, let me talk a little bit more about search tree nodes and what they may store. So some of the things you may want to store in this search tree. So for example here, this node created this node, right? So that may be the parent. So this node here may represent starting at state A and then moving to state D. That's what this node represents. Nodes are in a path along the search tree. They are not just a state. So we may want to store in these nodes the state. So that's the state of the environment that this node represents. We may want to store the parent node. That is the tree node that generated this node. And what we can do with that is, for example, when we want to know the path that created this node, if we've gotten to the goal node, then we can go back through the parent pointers to look at the actions to see what that path is. We may want to store the action that produced that node. We may want to store the path cost so far from the start, right? We could store that. And the cost of the path so far from the start to a particular node n, traditionally, that's called g of n. Why it is g, I don't know, but it is so ubiquitous that we're going to stick with it. Okay? So g of n is a node, and g is the path cost so far of all the actions that we've done to get to that node. Similarly, we may also want to store, for some reason, the depth. So the depth of the search is the number of actions we've taken so far. So remember, because action costs can be arbitrary, the cost of this node is not the same as the depth of the node. But if we did have, for example, all costs equal to 1, then the cost would equal the depth in that special case. Maybe, if we talk about this in the future, you could have things like other pre-computed data or optimizations like legal actions, heuristics, whatever. But here's what we want, basically, for the most part, is to store these things. And the important distinction, again, of node versus state. State is a configuration of the environment, and a node is a bookkeeping data structure that only exists within the search tree to keep track of where we are in the search so far. Nodes are on paths in the search tree. So this is the visualization that I want to give here. So this node E, right here, you could say, oh, that's node E, or that's state E. That would be a bad way to visualize this. How you should describe this node is via the path that it took to get there, right? This node represents starting at A, then moving to D, and then moving to E. That's what that node represents. It's a path through the search. It's not a single state, it's a path. So the G cost of E, put your hand up if you could tell me what the G cost of this node would be. Hand up, don't just yell it. Yeah. 2. Why? Because the path cost of A to D, so the G cost of the root node is going to always be 0, because we haven't gone anywhere yet. Then the G cost of AD is going to be 1, because 0 plus 1. And then we've gone from D to E, which is another 1. And so you're correct in that the G cost of this node, representing the path ADE, is going to be the sum of the action costs up to that node so far, which is equal to 2. So good. We're all on the same page. Great. So that's the difference between nodes versus states. And I drive that home because there's always a couple of people who do have that mixed up. Now, the next concept is this concept of the fringe. Okay? The fringe is we're going to change the name of the fringe later to the open list, meaning the nodes that we haven't expanded so far. Okay? But for now, we're going to call it the fringe because that's what the textbook calls it. And these red nodes here are ones that we have already chosen to have expanded, right? So we expanded A, this root node A. Then we expanded the node A to D, right? And now we are left with this. So nodes that have been generated and added to the search tree but have not yet been chosen for expansion are what we call in the fringe. The fringe is sort of the leaf nodes of the search tree, okay? And it's also called the open list. So the leaf nodes that are white in this diagram, so if we color the expanded nodes red, then the ones that are white are the leaf nodes in the tree, also called the fringe. So that's all we need now to put this into an algorithm. So let's look at that algorithm. In the book, this algorithm is called General Uninformed Tree Search. Uninformed means that we have not inserted any extra knowledge into this algorithm. So for example, if you gave me the problem of going towards that door, right, uninformed tree search would try every possible action. As a human, I might try the actions that take me to the left before the actions that take me way over there because I have some knowledge of directionality and stuff. When we get to assignment 2, that's what we'll be doing. That's called heuristic search. We're going to make heuristics that help guide us toward the goal. But for now, this is uninformed. That type of search is called informed when we have guesses. So uninformed tree search. So we have this function. It's called tree search. We're going to take in the problem. Now, in general, you're not going to have an actual variable called problem, right? You're going to have an environment like, a pathfinding environment or whatever. We're going to have problem. That defines the rules of our environment. And we're also going to have a strategy. And we're going to talk about search strategies in a couple of slides. But search strategies are the things that tell us which node to select from the fringe in order to expand it next. And that strategy is going to define the overall behavior of the algorithm. But in general, here's the algorithm. We create the fringe. The fringe initially is going to be just a node containing the initial state of the problem, right? That was that A up at the top, that root node. Now, while true, there's just a couple of lines of code here. If the fringe is ever empty, then fail. If we can't do anything, if there's nothing left to expand, and we haven't gotten to the goal yet, then we can never possibly reach the goal because there's nothing left to expand. So, fail. If the fringe is not empty, then we select a node from the fringe to expand next. Okay, that we're just going to label this node. If the state of that node is the goal state, then we have found a solution. So here it just says return solution, which means it is possible, right? In your assignment, you're going to actually build the path and then return the path, right? Or return the cost or whatever. But here, this problem doesn't say anything about optimizing the cost or anything like that. It just says return solution. So a solution is possible. It said, up here, it said, if we don't have anything left to do, then it's a failure. Down here, we return solution or success. But in our assignment, we will be actually calculating the solution, not that just that there is a solution. If this current node is not the goal, however, then what we do is we say add the expansion of that node to the fringe. Okay? So we're going to have this function called expand that's going to generate the next few nodes that we're going to add to the fringe. So let's look at that expand problem just a little bit, or that expand function. So this function takes in a node, and it takes in a problem definition. That problem definition just contains the legal actions and stuff. So what we're going to do is we're going to have an array or a collection of successors. So the successors are going to be the children of that node in the search tree. Then, for each legal action A from the state of that node, so for every legal action that we have, we're going to first, this S should probably be an N, I apologize for that. So we're going to take the state of the node and do the action A at that state, right? Then we'll create a node of the resulting state, and that's going to be, well, that's eventually going to be added to the successors. So this S, that's going to represent the next node. Then what we do is we set the parent of that node, S, equal to the node that we're currently iterating over. So set the parent equal to the node that generated this one. Then take the action cost of the action that generated this, so A, and we add that cost to the G cost of the parent node to get the G cost of this node that we just generated. Then we set the action equal to A, and maybe set the depth equal to depth plus 1, for example, and then we add that node to the successors. Okay? Now, who can tell me a little error that I have on this slide? Because I haven't noticed it in the 7 years that I've been teaching this course, but I just noticed it. It might not be obvious, but here we've taken s.action.cost, but then on the next line, we actually set what the action is, right? So this should just be a.cost, right? So just take a.cost. But it's still the same thing. This is just pseudocode. It's not meant to compile or run. But basically, we take every action that's legal at the state represented by this node, do the actions to get the next state, generate a node based on that state, set the g-cost, set the action, set all the bookkeeping stuff, and then return that. So then we return the successors, and if we look back at the previous slide, if this returns all the successors, then the successors get added to the fringe, right? So the pseudocode is always a little more complicated than how it looks visually, but this is what you're going to be doing, basically, in assignment 1. And this is the root algorithm of all search algorithms. They all come from this algorithm. However, they, more complex, there are people like me who write their PhD thesis on different search algorithms. And so obviously, they're not all this simple, but this is the root algorithm that we use for all of our algorithms. So now that we have that algorithm, as good computer scientists, we're going to talk about the properties of how they solve those problems, right? So the problem-solving performance. And there's going to be 4 measures that we use to discuss the problem-solving performance of these algorithms. The first is called completeness. An algorithm is complete if a solution exists, it is guaranteed to find a solution, right? So if a solution exists and it's guaranteed to find it, the algorithm is called complete. If there's even a remotely small possibility that it may not find a solution, if a solution exists, then it is called incomplete, right? So this is kind of a worst case thing. If there's a possibility at all that it doesn't find an existing solution, then it's incomplete. Next, it's optimality. If it finds a solution, or when it finds a solution, does it find the optimal solution, right? Because if we look back at that algorithm, it's going to say return solution. It doesn't build up every possible solution and then later compare them all. It just returns this solution. So all of that type of algorithm is going to return the first solution that it finds. And if it is guaranteed to find the optimal solution, then it's called an optimal algorithm. So that's the optimality. So if I ask you, is this algorithm optimal? Well, we'll talk about that in a second. It means that it finds the optimal solution always. If there's an algorithm that can find the optimal solution, but has, even again, that 1 in a trillion chance of not finding the optimal solution, then it is not optimal. This always has to be true in order for it to be optimal. Next is, of course, the big O, time complexity, right? So we have to talk about how long does it take to find a solution, and time complexity is going to be measured in terms of the number of nodes that we expanded, right? So how many nodes do we expand? And then space complexity, how much memory is needed to actually run the search, right? So all of these are obviously very important. And because we're going to do some of the analysis on this, the example I gave last time, if your boss asks you to find a path, well, which algorithm are you going to pick? Well, do you have to have it be optimal, or can it be a little bit suboptimal? Does it have to run in under this amount of memory? Well, this is the type of analysis that you'll do. You won't just try every algorithm and measure a bunch of experiments. Let's do the analysis first. The time and space complexity is measured on the size of the input graph and the problem. Time measures the number of nodes that were expanded, okay? Or number of nodes generated, depending on the algorithm. The space is measured by how many nodes we have to store in the worst case at any given time, okay? Do we need to store that whole graph search tree? Well, that thing was infinite. That's pretty big. So if we have to store that whole thing, that may not be great. So search, especially AI search, traditionally measures, here are some definitions. So the branching factor B. So if you think of a tree, it has branches. Some limbs can have 10 branches, others have 50 branches. So the branching factor B is the maximum successors at any given node. So if I'm talking about a problem where I can move up, down, left, and right, then the branching factor B is equal to 4. Okay? We talk about depth D. That is the shallowest goal node. So as we go different depths of the search, D is the shallowest goal node. And so if we have at each depth, or at each node, B maximum successors, and we have depth D, then that's going to be B times B times B times B times B as we go down. And so we have this exponential size of the tree, B to the power of D. Right? So the tree, that's how big the tree is going to be. Okay, so that's kind of the first half, just putting a little recap here and possible exam questions for you. So problems are defined by the initial and goal states, actions, and cost function. An optimal solution has the lowest cost function among all the solutions. Search finds a solution by exploring the search tree. It generates a search tree by exploring the state space, but I'm sure you know what I mean. The search tree consists of nodes and edges. Nodes in the search tree are not equal to states in the problem. And problem-solving performance is measured by these 4 things that we just talked about. Okay, so the real thing that's remaining in that general search algorithm is the search strategy. Which node do we select from the fringe in order to keep going with the search? So there's 2 types of search. I've alluded to this already. There's uninformed search, which is also called blind search, meaning that you have no additional information. So you have no info about the states beyond just the legal action description. And so you're limited to successor generation and goal testing. So you can generate the next states, you can tell if you're the goal, but you can't tell, for example, how close you might be to the goal, or a guess at how close you might be to the goal, etc. Informed search, or heuristic search, as I call it, and many people call it, you can guess which states are sort of more promising and hopefully lead you to the goal faster. Okay? And we'll get into all that when we approach that lecture, I think in about 2 weeks. So the first algorithm we're going to look at is called breadth first search. And I'm sure everyone here has already seen breadth first search, and you're saying, it took him 40 minutes to get to breadth first search, what is he doing? But you're going to see now, hopefully, why I did all of that. So in breadth first search, the root node is expanded first, right? Then the root successors are expanded next. Then their successors are expanded next, etc. So this English description of BFS, in general, all nodes at a given depth are expanded before any nodes at the next depth. That's why it's called breadth first search. We do the whole breadth of the depth, right? And then we do the next one. And in order to accomplish this, all we have to do to that original algorithm is use a queue for the fringe. Okay? So hand up if you can define a queue for me. Oh, okay. I'm always going to ask for a hand up, and if you just say it, then I'm going to call on someone else. So I always want to ask different people. In the back there? First in, first out. That's what a queue is. That's the most basic, correct definition that I can think of. So if you think about it, what was happening is we added the root node, then we add the root node successors, right? And then the root node successors are going to be next in the queue, so those are the ones that we take out next. And so using a queue for the fringe accomplishes depth first search. So just watch this. This is the general uninformed tree search problem. This is breadth first search. Right? All we did is use a queue for the fringe. And then down here, we just pop off of the queue. So if you think about things, when you add to a queue, if you think of a queue as an array, then you add things to the end of the array and you pop them off the front, right? That's just like a queue. Like if you're British, a queue means a line. You're lining up for something. You take people off the front, you add them to the back. That's it. That's breadth first search. You already knew it. It's just a queue for the data structure. So let's have a look at BFS in practice. Here is our root node up here. That is the initial state of the problem. Then we expand its children. Then this was the one that was put into the queue first. So that's the one we expand next. This one is next in the queue. so we expand that one next, and then so on and so forth. These were added from left to right to the queue, so we go, sorry, I didn't want to go there. So we would do this one next, then this one, then this one, then this one, and you can very easily show that this will guarantee to expand all of the nodes in the breadth of a particular depth before you go to the next step. Okay, so that's why it's called breadth first search. Now, you may have been taught breadth first search with a recursive algorithm, right? I think maybe 90% of people, if they're taught BFS, it's a recursive algorithm. It's the same performance properties as this one, okay? In a recursive algorithm, what you're doing is you're using the program stack as the fringe, essentially, when you do that. So it's the same algorithm, just there may be fewer lines of code in a recursive algorithm than in this. Okay, so let's have a look at this. This is the environment that we're going to be using for assignment 1. It's an environment in which there are some different colored, so we are on a grid. For assignment 1, we're going to be able to move up, down, left, and right. For assignment 2, we're going to be able to move in 8 directions. So we're going to add the diagonals to that. And so, for example, if we start down here at this yellow node, and the other rule is that we cannot go from one color node or one color state to another color state. Just, we can stay in the water or we can stay on the land, essentially, if you want to look at it that way. So if we start down here at this state, then if we are doing 8-directional search, for example, we will expand the successors of the root node first, then there's next, and there's next, and there's next, and there's next. So that's what breadth first search looks like at that level. So let's talk about the problem-solving performance of breadth first search. All right, BFS performance. Breadth first search, good news, it's complete. That's good. So BFS is going to eventually explore the entire tree. So if a node contains a goal state, and so whenever I say goal node, that's what I mean. The state of the node is the goal state. So if it contains a goal, it will find it eventually. BFS will find the shallowest goal node in terms of depth. So since it explores all nodes at a given depth, before it goes to the next depth, then it's going to find the goal that has taken the fewest actions to get to. All right. But that means that BFS is not optimal. Okay? So in general, BFS does not produce optimal solutions since the shallowest node, meaning the fewest actions, is not necessarily optimal. BFS is optimal only if path cost is a non-decreasing function on depth. So you can think about that for a little bit and what that means. But the easier way to think about it is that if all action costs are the same, then BFS is optimal. But in general, it is not optimal. And let's look at this example we've been doing the whole time, right? So if we do BFS and the goal state is C, then there's a path A, B, C, right? So as we generate, okay, I'm going to start up here. Let's apply our algorithm. We're going to expand A and put its successors into the fringe. Okay, there's no goal yet. We expand D, put its successors into the fringe. Then expand B, put its successors into the fringe. And we do not return a solution until we take the node off of the fringe. That's very important. And we'll see why that's so important later. But at the time we generate the node, that is not when we test for the goal. Only when we pop it off the fringe. So this is not the goal, this is not the goal, this is not the goal, this isn't, but this is, right? So BFS will stop right there and say, I got a solution, it's A, B, C. But because we're humans and we can process this really quickly, we can see that even though that has the minimum number of actions, it does not have the minimal cost. So optimality here is in terms of cost always. So A, D, E, which we would find later if BFS kept going, but it doesn't, has 1 plus 1 plus 5, so that has a lower cost of 7. So that's actually the optimal path. And so BFS in general is not optimal. Now you could say, okay, well it's optimal a lot of the time, right? Maybe a lot of the time it will find the optimal path, but if it's not guaranteed to find the optimal path, which if you can generate an example where it doesn't, then it isn't guaranteed. So if it's not guaranteed, then it is not optimal in general. Let's talk about time complexity. So each state has b children. If we have a goal at depth d, then we have b times b times b times b, blah, blah, blah. And so we have big O of b to the power of d nodes generated, right? So really simple time complexity analysis of that one. That's exponential. That's pretty bad. Like that's not necessarily what we're looking for. Let's see if we can do better in the future. Space complexity. Oh, by the way, I'm coloring these green if they're desirable properties and red if they're not desirable properties. Okay, so not optimal is not desirable. Space complexity, also not desirable, because we have to store the entire search tree in memory. And what do you have more of, typically, when you're doing computing? Operations that you can do, or memory. Right? Memory is usually the bandwidth. I can run an algorithm overnight for 1 trillion iterations, no problem. But do I have a terabyte of RAM? Probably not. 5 years from now, when you're watching this lecture video for your refresher on BFS, you may have a terabyte of RAM. You may be laughing at me. But, you go one depth more, now you need 10 terabytes of RAM, right? So memory, that is the real hard case here, where we have an exponential amount of memory in terms of the number of nodes we have to generate and store. So that's bad. Let's look at an example of how bad that is. Let's say that we have a branching factor of 10. Let's say we can do 10,000 nodes per second. That's very, very slow. You should be doing a lot more than that if you're programming in C++. Let's say we have 1 kilobyte per node. And so this is what happens. If we have a search of depth 2, we're generating 1,100 nodes. That takes only 1/10 of a second. That's not so bad. And it uses a megabyte of memory. Okay, let's double the depth. Now we've got 100,000 nodes. It takes 11 seconds, and I'm using 106 megabytes of memory. Now let's just go to depth 10, right? Any reasonable problem that we couldn't instantly solve ourselves is going to go to at least depth 10, right? Because if you think about it, like, okay, I'm moving 10 actions. 10 actions is not a very long path. So here, 10 is going to be 10 to the 11. So what's 10 to the 9 is 100 million. Well, that's a billion. I guess it's a billion. So this is 100 billion nodes generated. It's going to take 129 days to do that, which is possible, but you need 101 terabytes of RAM, right? Which is probably not going to happen. I've got 101 terabytes of hard drive space, but maybe not RAM, right? So, okay, let's go one more. Now we're talking about Google data center type of storage, but you can't run it for 35 years, right? Or just go one more, right? It's exponential. Exponential is hard to think about. But just going from 8 to 14 goes from something you can run almost overnight if you have the RAM to something that is going to take years and years. Okay. Uniform cost search. This is the next algorithm that we're going to look at. You may have expected depth first search, but I tricked you. Okay. So BFS is optimal when all action costs are equal, because it expands the shallowest node first, the next thing that we put into the fringe. Uniform cost search is going to be the first algorithm that we look at that's optimal no matter what the costs are. And the reason is it's going to look through the fringe and expand the node that has the lowest path cost. So we go through every node that we've generated. Instead of just taking the one that we put into the fringe in the queue, we're going to look through the whole thing and find the one with the lowest path cost. And so if we look at the one with the lowest path cost, then that's the closest to the start. And so the one that's closest to the start, if we're checking that, then okay, that's going to lead us to an optimal solution. If all costs are equivalent, if all costs are equal, then this will perform identically to breadth first search. So that could be an interesting exam question. When does uniform cost search do the exact same thing as BFS? Well, it would be when all of the costs of your problem are equal. It works only if all costs are greater than 0, but just like this whole search algorithm business, if their costs are equal to or less than 0, then we can't make any guarantees anyway. And if you've ever heard of Dijkstra's algorithm, which is a single starting point to all possible other places, shortest path algorithm, UCS is equivalent to if you ran Dijkstra's algorithm to a single goal on the map, or in the environment. So now we're not only looking at uniform cost search and breadth first search and stuff, but we're comparing them to other algorithms. So if you look at Dijkstra's algorithm, maybe I should have included it, but it looks very, very similar to uniform cost search. Here's uniform cost search. The only line we changed is this one, right? We have a fringe. It's no longer a queue. The queue was for breadth first search. You can use whatever data structure you want up here. Typically, when we have algorithms that do things like pick the minimum value of whatever, we would use a priority queue or a heap or something like this so that we could get this out faster. So whatever your fringe is, could be just a normal array or vector. You look through that fringe, you find the minimum g-cost node, and that's what we pick. And that's uniform cost search. Same algorithm, we just pick a different node from the fringe. The search complexity, well, UCS is complete if B is finite, but of course we're only dealing with finite problems here. It's optimal if all action costs are greater than 0, so you may see this in some places, epsilon greater than 0, whatever. The time complexity, that's not going to be on the exam. I don't want to get in. I don't like doing a lot of math. I'm sure you don't like doing a lot of math. But the time complexity of UCS is actually a little bit complicated. It has to do with the optimal solution of the problem, and it's big O of B to the 1 plus the ceiling, or the floor, of the optimal cost divided by this epsilon. And in the worst case, that is much bigger than B to the power of D. So bad time complexity, uniform cost search. Next algorithm. And also the space complexity is equally as bad, right? Because if the time complexity you need to generate those nodes and store the whole thing, then the space complexity is equally as bad. Depth first search, the next algorithm that you've all heard of. It expands the deepest node on the fringe. Okay? So the search immediately goes to the deepest level of the search tree to a leaf node. And the leaf is a node that has no successors. And if a leaf is reached, it's discarded, and then the search sort of backs up to the previous depth. That is the visually intuitive way of describing depth first search. But algorithmically, all we have to do is use a stack for the fringe. Okay? Who can tell me the definition of a stack? Hand up, different person. Yep. Last in, first out. Yep. So the thing we take next was the thing that we most recently put on it. Okay? The way I remember a stack is a literal stack of plates. Right? If you put plates in a stack, when you go to get a plate, you're not going for the middle one or the bottom one. You're taking the one that you most recently put on the stack. It's a literal stack, right? So usually, DFS is implemented as a recursive function, but we are also going to look at this version. This is depth first search. We have a stack instead of a queue. This is depth first search. This is breadth first search. Right? You may have learned both algorithms before, but I doubt you've seen them expressed so similarly. Right? The difference between these two algorithms is literally just how you take it off of the fringe. Depth first search, you take the one on the right. Breadth first search, you take the one on the left. That's it. That's the only difference between BFS and DFS. And not Tuesday's lecture, but Thursday's lecture, I'll talk about implementing this in C++ and why some implementations are absolutely terrible and you should never do them, and some implementations are much better, and sort of how to get around that. Not only for C++, but languages in general. Because stacks are really nice, right? If you take from the end of a vector or the end of an array, that's just, bloop, take it off. But if you take something out of the beginning of a vector, well, now you have to shift everything over, and that's a linear time operation, right? So we'll get into all those implementation details, but theoretically, this is what it is. So BFS, DFS. Look at that, it's cool. Right? All right. There's also a recursive depth first search implementation. And the reason I'm giving this is because I'm going to be talking about another algorithm, and that algorithm is much more easy to implement as a recursive algorithm than trying to frame it in terms of the algorithm we just talked about. So this is depth first search. You take in a node and the problem description. This is the recursive function. If the state is goal, return solution. And in actual fact, The only difference between the recursive implementation and the iterative interpretation is that there's no while loop. Instead of the while loop, you just call itself. That's basically it, right? So if the node is a goal, return solution. And we also don't check to see that the fringe is empty, because if the fringe is empty, it just won't be called again. So DFS, recursive, recursion is a little bit different. So the successors, we expand the problem. For each of the successors, we are going to call DFS on that and the problem. And then initially, what we do is we call DFS on the root node. Okay? Someone is sort of repeating what's on the slides, and it's a little bit distracting. I can hear you talking, so please, if you don't mind not talking. I generally don't mind, but I just hear it back to me, and it's hard to speak when you hear an echo. The performance of depth-first search. Depth-first search, it's not even complete. Terrible, right? It's not complete. You can easily enter an infinite loop. A, B, A, B, A, B, A, B, all the way down. Infinite loop. DFS is pretty dumb. Now, you can make some enhancement to it, we'll talk about it later, that make it sort of complete, but DFS is not optimal either. Like, it's way less optimal than BFS, right? Because if we happen to find a solution, it could be of any length. So we're not guaranteed anything. Time complexity is even worse than exponential, because we could find the worst depth solution, not the lowest depth solution. So if M is the maximum depth of a node, that may be the time complexity of depth-first search. And you'll see this expressed in a hilarious way when you actually do assignment 1. But we may have to generate the entire tree. We can no longer talk about breadth-first search. You can think of breadth-first search almost like a snowplow, right? It like checks everything and everything. Nothing can get past it. But things can get past depth-first search. However, depth-first search, space complexity. Oh, space complexity. You can actually run the damn algorithm, right? You can't run BFS. You can run DFS. So that's where it gets cool. It only has to store the current path that it's on. It does not need to store the entire tree. Okay? So it uses B times M memory, where M is the maximum node. And it stores the successors of the node in the path. And this is like the branching factor. So we may, that branching factor B, I'm going to generate the successors at this depth, then go down one node, generate the successors at that depth, go down one node, generate it, right? So we have B times D. So here's sort of a visualization of what breadth-first search may end up looking like. But what we've done in this visualization, we've taken out the possibility of going A, B, A, B, A, B, because that's not super interesting. But what it does is it goes all the way down a path until it can't anymore. And then if that's not the solution, it will back up, like it's doing right now, to go down the next path. Okay? So breadth-first search, you saw it go out in all directions at once. Depth-first search is like a laser beam, goes all the way down one, tries to find it. If it did, great. If not, it has to go back up and then down another path. Okay, so this is what DFS looks like, and I might as well give it the satisfaction of finding the goal. Computers are people too. There we go. Okay. Now, how might we solve some of the problems of depth-first search? How do we prevent it from getting lost down this infinite hole that we don't want that to happen? Let's apply a limit to the search. Okay? That limit is going to be called L. And what we're going to do is we're just going to say, once you get to depth L, no more searching for you. It's just done. Okay? So you can do this in a number of different ways. The official way you would do it is to say, okay, if we're at depth L, and depending on how you do it, you're either equal to L or greater than or equal to L, whatever. We just have no successors past that point. Okay? So we stop the search at that point. This solves the infinite path problem. Right? Because we can no longer go A, B, A, B, A, B, because we're stopped at L, or L over 2 of those. So it will search the entire tree up the depth L. But of course, it introduces a new problem, which is that it's incomplete if the solution is past L. Right? So if we chose L equal to 15, but the first solution is at depth 20, we won't find it. Right? So that's another problem. The time complexity, however, got a little bit better because it's now b to the power of L, which is the limit that we've chosen. It's no longer the maximum possible limit, the maximum possible depth. And the space complexity is still great, right? It's even better, which is b times L. So it's a linear space complexity. So this algorithm is very runnable. Let's have a look at the algorithm of recursive DLS. So this is the recursive algorithm of depth-first search. And all we've done here is add this one extra line, which says if the current depth is greater than L, or greater than or equal to L, or however you want to choose it, because sometimes depth starts at 0, maybe you start depth at 1, you're just searching up to L. So if depth is greater than L, we're done, return. So this return statement, we're not returning anything, we're just stopping the recursion at that point. That's what this return statement is doing. So it's gotten to L, it will search no further. So that's all you need to do to create depth-limited search. However, the next problem, which you may have been thinking about already, is how do we choose L? I'm just going to say 15. I'm going to say 1,000. Am I going to say the amount of memory that I have? How am I going to choose L? Maybe we do some maximum path length analysis. So if my environment has 1,000 states, maybe I can choose L equal to 1,000. Maybe that's one way of doing it, trying to look at the problem and derive some properties. But we're doing uninformed search here. We don't want to have to look at the property, the environment, and analyze it. Maybe we have some sort of diameter of the search space, so if we have a certain maximum number of actions, maybe that could factor into it. Maybe the number of states in the problem. But let's not look at any of that stuff yet. Let's just let the search figure it out. How can the search figure out L? Any hand up, have an idea? Maybe you've seen this algorithm before? Okay, good. So we're all about to learn something. Iterative deepening, depth-first search. Iterative deepening, hopefully, that tells you what's about to happen. Let's just gradually increase the depth limit. Try 1. Oh, we didn't find anything. Try 2. Didn't find anything. Try 3. Didn't find anything. Okay, up to some value. The goal will now be found at the shallowest depth of any goal, just like breadth-first search. Because if it was any shallower, we would have found it at the shallower depth. Because we're searching the entire tree up to depth D, we're just using depth-first search to do it. So this has the completeness and optimality of breadth-first search. Because even though it doesn't expand all the nodes of a particular level first before going to the next one, we are guaranteed that for a particular depth, it will expand all of the nodes up to depth D, just like breadth-first search. So it is guaranteed to find a solution because it will eventually get to the depth of the solution. And just like BFS, it will be optimal if the action costs are the same. But in general, it is not optimal, right? It has the space complexity of depth-first search. That's awesome, because it means we can actually run the thing, right? So even though it has the completeness of optimality of BFS, which were better than DFS, it has the space complexity of DFS, which means we can actually run it. Let's look at the time complexity. You may think to yourself, oh wow, the time complexity is way worse than breadth-first search, because in breadth-first search, we're basically going to expand all of these nodes once, right? We're just going to go one depth, next depth, next depth, next depth. But here what we do is at depth 1, we expand the root node and stop. At depth 2, we expand the root node again, and then these two, then stop. Depth 3, we expand the first and second again, and the next one, and then stop, right? So every time we do a new depth, we do all the work that we did before in this one. However, if you amortize that time complexity, if you look at this best possible case of a branching factor of 2, which is the lowest you can really have, right, if it's an interesting problem, look at the final depth. How many nodes are in it? The number of nodes in the final depth is equal to the sum of all the other nodes plus 1. Always. Right? Because you're doubling it each time, and you're doubling and doubling and doubling. So this one has 1, 2, 3, 4, 5, 6, 7, 8, 16 the sum of all the others are only 15. So it may look like you're doing a lot of extra work, but in practice you're not. So the number of nodes search, you have D, which is the shallowest goal. You're searching the root node, D times. You're searching the second depth, D minus 1 times. You're searching the next depth, D minus 2 times. And if you look at this, D times B plus D times 1 times B squared, whatever, up until B to the power of D, well, big O time complexity, when you're talking about exponentials, only cares about the biggest exponential. And the biggest exponential is the final one. And so time complexity is the same as breadth first search. But in practice, I'll talk about that in a sec. It has the same time complexity, theoretically, as breadth first search, but in practice, it usually does about double the work, right? But double the work is basically just equivalent to one more depth, right? So it has the space complexity of DFS, which is awesome. In practice, it generates about twice the nodes, and so in general, because BFS has memory complexity that is exponential, and ID-DFS has a memory complexity that is linear, but has the same theoretical properties, we would want to use ID-DFS for problems that are going to be bigger than our memory can contain, right? So if you go out into the real world and you want to apply BFS, and your problem is huge, and you're going to run out of memory. So if you really, for some reason, want that behavior of BFS, but you want to actually be able to run the thing, iterative deepening, depth first search is your answer. Recursive depth-limited search looks something like this in its full form, where we check this cutoff just tells us whether or not we have found a solution up to this point. So I'm going to say cutoff occurred equals false. That's going to be set to true if we have searched everything up to L. So if the state is a goal, then I've found a solution at its shallowest depth, so return that solution. Otherwise, if the depth of the node is greater than or equal to L, we return that we have a cutoff, so we have searched everything. Then if that has not happened, then we expand all of the neighbors of this node, and then we call DLS on the child, the limit, and the problem. If the result of that was a cutoff, then a cutoff occurred equal true, and if the result was not equal to fail, then we return the result. Okay? So this essentially just does that. Okay, if we're searching up to a given limit, we have either found a solution, or we have run out of things to search, or we have reached a depth cutoff. Okay? We're going to actually use that because if we found a solution, we can stop the search. If we reached a depth cutoff, it means that I have to go one deeper. But if I have legitimately run out of things to do, then I know that I can stop my search because I've searched the entire problem space. So those are the three possible outcomes of a depth-limited search. And then iterative deepening depth-first search is just iteratively calling that function. So iterative deepening depth-first search, for D from 1 to infinity, you just OR your time limit. You start at depth 1. You call DLS with the root node and D, which will initially be 1. If the result was not equal to a cutoff, meaning that if we found a solution or we searched everything, which means there is no solution, then we return that result. Otherwise, it doesn't actually say an otherwise here, but if that is not true, then we just go to the next depth. And we go to the next depth and the next depth and the next depth. So if the first solution is at depth 6, we'll find it at depth 6 with this algorithm. So if we compare all these search strategies, right, we have this nice table of results. And so this table of results, I'm going to highlight the good ones here. So BFS, it is complete, and it is optimal if all action costs are equal. Uniform cost search is complete, yes, if B is finite, and if action costs are greater than 0. And it is optimal only if, or it's always optimal, sorry, so that's good. Iterative deepening depth-first search has the same properties in completeness and optimality of breadth-first search, but it has the space complexity of depth first search, which is great. So that's what we want. So that's why, in general, we may want to use iterative deepening depth first search instead of breadth first search. We will not be actually implementing iterative deepening depth first search in our assignment, but theoretically you would have to know, for example, why would I want to use that over breadth first search? That's a great exam question. Okay. So just a quick note that I'm about to talk about two different algorithms. One is called tree search, which we have been doing. Another one is called graph search. That's just what they're called in the book, but they're essentially the same algorithm. And I know there's a lot of terminology. I've thrown a lot of algorithms at you. I don't expect you to all remember them right now. But when you go back and you look at the differences being one line of code, it's actually pretty easy to remember all the algorithms, and you'll get surprisingly familiar with them. So in this book, which is an optional book, these are the names that they're using. So if you want to follow along with the book, you won't get lost. But the names are not important. The concepts are. So we looked at that example of depth first search going infinite, right? Going from A, B, A, B, A, B, A, B. One of the most important ideas in search is how to avoid that. We don't want it to go back and forth, back and forth, back and forth. And this is especially important in environments where you have reversible actions, meaning I could move to the right and then I could move back to the left and end up in the same spot. So most infinite loops and wasted time can be avoided by simply not returning to states that we've been before, right? If we think about the properties of our environment, would an optimal path ever visit the same state twice? Right? If it has a non-zero positive action cost, revisiting that state would just add to the cost. So by definition, if we go back to the same state, we have a worse path. So this is the idea here. So we can remember nodes that we have expanded and then don't expand any other nodes that have the same states as those nodes. And this can lead to an exponential savings in the number of nodes generated. Saving exponentially is exactly what we want. And the way we're going to do this is implement something called the closed list. So the closed list is just a list of states that we've already expanded. That's it. We just keep track of all the nodes that we expand, and we write down the state of that node so that we know never to create another node with that state. So the closed list stores expanded states, not nodes, but states. It is often implemented as like a hash table or a dictionary for efficient lookup, but we could just have a vector of all the possible things that we've seen. And so what we're going to do is just check to see if the state of a node is in the closed list before expanding it. That's it. So what we're going to do, because this is called the closed list, then the open list is going to be the fringe of unexpanded nodes. So the the fringe that we've been talking about so far, we're going to call that the open list from now on. So we have the open list of things that we want to expand, and we have the closed list of things that we've already expanded. And in practice, in assignment 2, we're going to be implementing this open list as a priority queue, which is sorted based on our search strategy. Okay, so this is what we just did. That's the exact algorithm that I had on the other slides, but as foreshadowing, I just included some white space here. So this is the algorithm. We have an open list. That stores all the things we haven't expanded yet. While true, if we have nothing left to do, that's a failure. Otherwise, I select something from that open list. If that's the goal, return the solution. If it's not the goal, expand the node and add it to open. In order to add a closed list to this, all I have to do is add some sort of data structure for the closed list. Maybe it's a set, maybe it's a dictionary, maybe it's just a vector, whatever, doesn't matter. And down here, if a node is not the goal, before we expand it, check to see if the state of the node is in the closed list. If it is, then continue. So that means that don't expand the children of any node whose state is already in the closed list. And if that is not true, so it's not yet in the closed list, right before we expand it, add it to the closed list. That's it. So we're just checking to see what we have done so far, and don't do it again. So this is that algorithm now. We added a couple of lines, but it's not a huge leap to get to this point. And so the book calls this thing graph search. So we called the other thing tree search, right? So it's searching a tree. This is still searching a tree, but the book just calls it graph search. So I'm just going to leave it as graph search, and just know that graph search means closed list. If on an exam I were to ask you a question, I will say tree search without a closed list or graph search with a closed list. Like, I'm not trying to trick you up on that terminology. I'll be very explicit if I'm asking you a question about whether or not there's a closed list or not. So it's only called graph search because that's how it's described. It's still an algorithm that searches a search tree. It just uses a closed list to avoid searching of nodes that represent the same environment state. So in assignment 1, what you have to do is, and I'll get into assignment 1 in the next class. I'll show you exactly how to set it all up. But what you're going to do is you're going to use DaveGPT, because I've given you the solution to the assignment. It's right here. You copy that. You paste it. I'm not joking. You copy and paste this into your assignment, and then you turn it into JavaScript. That's assignment 1. And then do it again for DFS. But a really cool thing is you can do it in a way, like you can think, so as part of your algorithm, you're going to get this configuration object. Inside the configuration object will be a search variable. That search will either be BFS or DFS. So you could think that you would go, okay, if strategy equals BFS, do all of this. Else, if strategy equals DFS, do all of this. Or you could do it the way I'm going to ask you, and only one line needs to change. So you could just write the algorithm and then have the if statement around that. Okay? Now, technically, in JavaScript, you would not change this line of code because you can just use a JavaScript array. That's fine. But down here, in JavaScript, open.pop gets something from the back. Okay? So that would be a stack. So open.pop would be DFS. And then open.shift in JavaScript would be BFS. It's literally like 4 characters of code difference between BFS and DFS. And I'll show you exactly where that goes in the assignment. The assignment is going to have a user interface. You don't need to worry about that too much. It's just for debugging. And you will implement both DFS and BFS, and you'll be able to see it beautifully visualized and all sorts of stuff. So tree search remembers nothing. It will re-expand states multiple times. That is bad. Graph search remembers the states that you visited and will never re-expand a node that has the same state as one we've expanded before. And so again, just to drive it home, tree and graph search, just to name, one has closed list, one doesn't. That's the important part. So what is the complexity of this? The time complexity. Holy crap. Well, it still retains the same. Well, okay, let me just go in the order that I have the slides. The time complexity is now amazing. If we cannot re-expand a state, then it's just the size of our problem, right? So if we have 5 states in our problem, then the time complexity is big O of the number of states, which is insanely good. So each state is expanded at most once. So in the worst case, we're going to expand every state in the environment. And in most cases, that's far less than the big search tree that we had before. And it's going to be the same upper bound no matter which search strategy. So if that's BFS, if that's DFS, if that's UCS, if you don't re-expand the states, then you're good to go. The space complexity is also big O of the number of states, right? So we have to store the entire search space in memory, but the amount of nodes that we generate is just equal to the number of states. So it's better, but this is often sometimes still a bit too much. Like if we have every square meter of the Earth, that's still a bit too much to have in RAM, but it's way better than what we had before, right? But if I'm using a search strategy like DFS, then it has the search complexity of either big O of the number of states or DFS, whichever is less, right? So whichever search strategy you use, that one is still going to be the overruling space complexity factor. However, graph search may no longer be optimal. Whereas if you had an optimal solution before, this one may no longer be optimal. It is a very tricky thing to describe because it depends on the underlying algorithm. Once we get into the A-star algorithm, I'll be revisiting this issue. But when a repeated state is detected, that means that the algorithm has found another path to the same state. If it finds another path, that path may actually be a better path. But we've already found the other path, which is worse, and we've told it not to revisit it. Right? So that can be bad. So graph search keeps the original path and discards the new path. But the new path may be the better path. So it's only optimal if we can guarantee that the first solution found is the optimal one. So that means uniform cost search, that always works. Because if the first thing that we find is the optimal one, then it's still optimal. But with BFS, it's not necessarily the case unless the action costs are the same, right? So if I ask you, hey, graph search with the closed lists may no longer be optimal, when is it actually still optimal? So that's a problem. It still maintains the completeness property, but it may not be optimal. So there's always these trade-offs in search between memory, time complexity. When we get into heuristic search, there'll be all sorts of new trade-offs that we have. But this is basically all you need for assignment 1. And in the next lecture, I'll show you how to set up assignment 1, how to do it. And you only have a week for assignment 1, but it's like 20 lines of code. So assignment 1 is all about getting used to the assignment infrastructure. And then every subsequent assignment will be the exact same infrastructure. And so then you'll be used to that. So assignment 1 is kind of easy algorithmically, but you may take a while to get used to the programming interface. Thanks.